I said it is very difficult to add something to what has already been said about our friend Sergio Bitanti. Should I use only 3 terms to define him? I would say scientist, gentleman, and friend. And we all know that he has been and is a reference person for the whole Italian community in automation and in system theory. I would just like to add that, with much pleasure, that Sergio has been and is frequently at Bologna University, where his last lecture last year has called a remarkable number of persons and many very positive comments. I would like to remember Sergio that he is already booked for another second conference, maybe next year or at the end of this year. Don't forget it. So it's okay. Well, I will simply tell something about the role of geometric aspects in errors in variables estimation and identification. I will touch many different topics, so I will be able to use only a few words for every topic. Don't be frightened by this long list. Starting from the very beginning, the errors in variables context concerns a situation in which we have observations that are corrupted by an additive noise, an additive error. If we define a matrix with our observations and consider the corresponding matrix of noiseless observations, the linear relations, if any, connecting the noiseless quantities, can be found in the kernel of this matrix X cap. This is very well known, of course. Usually some additional assumptions are considered because otherwise we would be able to associate almost any linear relation to any set of data. Typically, it is assumed that the noise terms have a null expected value or even mean value, like in this case, that the noise sequences are not correlated with the noiseless ones. And under those assumptions, the additivity property concerning the matrices of data can be transferred to the sample covariance matrices or matrices. Thank you very much. The second one, okay. And so we can look at a problem, an algebraic problem of this kind. We have in our hands a covariance matrix of observations. What we are trying to do is to decompose this matrix into the sum of 2 other matrices, one matrix of covariance of the additive errors, and one positive semi-definite matrix that will define, if possible, one or more linear relations. Of course, the matrix sigma of observation will be positive definite, the covariance matrix of the noise could be positive definite or semi-definite, and the sigma cap, the matrix sigma cap we are searching for should be a positive semi-definite in order to define linear relations. A further simplification of this problem has been introduced by the Nobel Prize Ragnar Frisch back in 1934. Frisch considered errors mutually uncorrelated, and this simplifies a lot the problem because in this case the covariance matrix of the noise is a diagonal matrix. So the first problem we could define or consider is, should we search for a solution in the noise space, searching for a set of covariances of the noise that satisfy this condition, or should we search for a solution or for solutions in the parameter space, in the kernel of the matrices sigma cap or X cap? It is not such a stupid problem because let's start considering the shape of the locus of solutions in the noise space. It has been shown that this locus of solutions is something like this, a convex surface or hypersurface that intersects the coordinate axis where only one of the variances is different from 0, is in correspondence with the least square solutions. Of course, the distance of this surface from the origin is linked to the amount of noise present on the data. If the noise is reduced, the surface will go near to the origin and will collapse onto the origin when the noise is zero. Well, it does not look at a first glance as the best place for working, for searching. And another problem that is of relevance is the following. When we move on the points of this surface, what do we find in the associated matrix sigma cap? Will we find just a single linear relation? Maybe there exist some points in which we have more linear relations. It is not clear a priori. And with reference to this problem, we have a very important theorem that says that every point of the locus of solutions corresponds to one and only one linear relation if and only if the inverse of the matrix sigma of noisy observations has entries that are all positive or can be made positive by changing the sign of some variables. Moreover, in this case, another extremely powerful theorem exists which says that in this case, if we go into the parameter space and normalize to one of the coefficients of the linear relations, all linear relations will be contained inside the simplex defined by the n least square solution. This is a very, very, very powerful result, and it would suggest to search for the solutions here instead than in the noise space. It looks more simple, more easy, more logical. Well, in fact, this simplex is very important also because its area gives us an idea about the difference of information that we can get from the different least square solutions, and can also explain how the indiscriminate use of least squares, even when we don't know much about the real situation, does not lead, generally speaking, to large disasters, but only to modest disasters. But very unfortunately, this situation is true only when the condition concerning the existence of only one linear relation compatible with the noise is true. In all other cases, the situation is completely different. And this simplex literally explodes. Think to a bomb, one moment after its explosion. It goes everywhere in all different orders. It is impossible to solve any problem looking at the solution in the parameter space. There are other interesting properties that maybe we have not the time to deepen. I will just mention that when we have one point of the locus of solutions in the noise space that corresponds to more than one, let's say to k linear relations, then this point is an accumulation point of points that correspond to k minus 1 linear relation, which in turn are accumulation points and so on and so on. So we have, however, a problem. We should search for a simple way to define the points of this locus of solutions and also to move on this surface without having the necessity of introducing excessively complex computations. And the solution is really very, very simple because we can try to parameterize the surface of solutions through the intersections of lines from the origin with the surface. If we take a generic point in the first orthant and search for the intersection of the line from the origin to this point with the locus of solutions, this intersection is given by an extremely simple result, which is this one, which was found by Margherita Pierantoni. It is given by this point C divided times lambda m, which is the inverse times sigma tilde C, where sigma inverse is the same for all points. It must be computed only once, and moreover, it is a symmetric matrix. And the sigma tilde C is just the diagonal matrix, the covariance matrix defined by this point. This way of parameterizing the singularity surfaces of covariance matrices has been used a very large number of times and is very, very effective, as you will see also in the following, in the solution of many problems. So we consider a generic point, we consider a line, the intersection is given by the expression that you have seen. Well, another important problem that remains unsolved for some time is the following. How many linear relations can be compatible with a set of data? In other words, which is the maximal dimension of the corank of a given covariance matrix sigma n? It is a very simple problem to be defined, but it is a bit more complex to be solved. And I need to introduce a small additional notation. Let's define as a singularity surface of the matrix sigma n bar R as the locus of points in the vector space RR that define a covariance matrix with this structure that subtracted from sigma n gives a positive symmetric matrix. The shape of the surface is the same we have already seen for a generic covariance matrix. Well, the result we are searching for is the following. The maximal corank of a given matrix is greater or equal than a given integer q if and only if the intersection of the singularity surface of sigma n minus q plus 1 and S of sigma n bar n minus q plus 1 is non-empty for every permutation of n minus q plus 1 variables. And this condition is very simple to be verified, just using the radial parameterization we have seen. And to check for the maximal corank of a given matrix, we must just verify whether this condition is satisfied for q equal 2, 3, and so on, until it is no longer satisfied. And we get the maximal number of linear relations. This problem is considered as very important in econometrics because we can construct models where the number of independent variables is minimal. Well, this is the situation, and it is extremely easy to verify the existence of common points, just checking the distance between the intersections with lines from the origin. It is an extremely simple problem from a computational point of view. Oh, now I remember we discussed, Sergio, with you something about this. We will try to solve, to perform a mission impossible. It has to find a solution in the context of the free scheme. It is, of course, impossible to solve this problem when we have just one set of data, just one data covariance matrix, because we have absolutely no. No, I was going in the wrong direction. We have absolutely no way to discriminate one point against another. We cannot define any reasonable cost function to say that one point is better in some way than another. But we can try to introduce this definition, which looks as extremely fancy, or even stupid if you prefer. It has given two covariance matrices of the same process. We could define this matrix as independent if the dimension of the kernel of their difference is equal to 1. It looks stupid because you will never find a condition of this kind. While on the contrary, I go back one moment, this condition concerning the existence of more linear relations for real data can be verified in some cases with data affected by noise. For instance, I checked it for the consumption of meat in the United States during the 29 crisis, and you can get clearly, not approximately, clearly a model with two linear relations. Well, let's return to this funny definition. Of course, should this condition be satisfied, you can easily imagine that the true model would belong to this kernel, but this does not exist. However, if we look from a geometric point of view to this condition, we will observe that two different covariance matrices of the same process will define singularity surfaces that will surely have common points, because at least the point corresponding to the true amount of noise on the data will belong to both surfaces. This is quite obvious. More generally, you will find that the number of common points is infinite. Usually you have intersections, like in this case, where you have infinite points that belong to both surfaces. And if you consider one of those points, since it belongs to both surfaces, you can use it to go back into the parameter space by considering it as belonging to the first or to the second surface, and consequently applying it to the first or second covariance matrix. And what you will get will be two different points in the parameter space, with, of course, one exception. And this exception concerns the only point that corresponds to the true amount of noise on the data. Of course, when you work with real data, also this will not be true. But you have, in this case, a powerful cost function to select the best approximation, because you can use the distance, the Euclidean distance between the points, the two different points that you get in the parameter space, as a measure to select the best approximation of the covariance of the noise present on the data. I would also like to remark that this condition of assuming that in practice the noise covariance data sigma tilde is the same on different sets of data is not so unusual in practice, because often you get data from the same set of sensors that on long sequences give approximately the same noise covariance matrix. Well, can we do something once we have tried to get a model, or for other reasons already have a model? Something useful, I mean, from an engineering point of view. Well, I would like to reply with the words of President Obama, yes, we can, but perhaps it is better to say, yes, we can try to do something useful. And, well, one thing that we are doing is to perform the optimal interpolation of our noisy sequences. And it is a very simple job, because if we define a vector in which we insert our observations, define with v cap the same vector with the noiseless data that, of course, we don't have, and define this matrix G, in whose rows you insert the shifted parameters of the model, clearly the vector v cap will belong to the kernel of G, and consequently G times V is equal to G times V tilde. This is quite obvious. And if we assume, for instance, that the noise has a Gaussian distribution, we can try to obtain the best estimate of the vector v cap, or to be more realistic, of the vector v tilde, and the expression that we can get is this one. And of course, this second term is the best estimate of v tilde, that subtracted from v gives the maximum likelihood estimate of v cap. The same result can be obtained in an even simpler way if we compute the minimal variance estimate of v tilde, and you obtain the same expression. So this expression gives, when the noise sequences are Gaussian, a maximum likelihood estimate. In all other cases, in any case, a minimal variance estimate of v tilde and of v. Well, which is the geometric interpretation of this result? It is simple to show by remembering the definition of oblique projection of a vector on a subspace along another subspace, that the expression, this term, is nothing else than the oblique projection of the vector of observation V on the subspace image of sigma V tilde times G transpose along the kernel of G. So this allows also some considerations that maybe we don't have much time now to explore. It is something like this. Well, how much? Good. What can we say about identification in the same context when we consider a dynamic system in which we have additive noise on the input and out measures, and just to respect also the Frisch conditions, we assume that this noise is wide. Well, with quite simple passages, we can arrive to an algebraic formulation of the problem which is almost equal to the formulation for the algebraic case. And moreover, we have an additive information to be inserted as to the order of our model. So assuming that the order is k, we will construct a covariance matrix of the observations that can be decomposed into the sum of the covariance matrix or sample covariance matrix of the noiseless data that we don't know, and in the covariance matrix of the noise that in this case will be defined only by the number, by a number of variances equal to the number of inputs plus the number of outputs. So the main difference with the algebraic case is that we have different dimensions in the noise and parameter spaces. And of course, also here we could repeat results that are practically the same of, well, we could first of all define the identification problem as the problem of getting an asymptotically unbiased estimate of the parameters and also the variances of the noises. One of the uses of the model could be, for instance, filtering, errors in variables filtering. The singularity surfaces that we can define for the matrix sigma k are the same that we have already seen for the algebraic case, but with a remarkable difference. We can start constructing the singularity surface for a model of order, say, 1. Here I am considering a single input, single output model, order 2, and so on. But once we reach and go beyond the correct order of the model, we will observe that the point associated to the true variance of the noise is common to all subsequent surfaces. And this is nothing else than the result we have already seen for the algebraic case concerning the presence of more than one linear relation. Because in this case, the matrix sigma n cap will contain not a different linear relation, but the same linear relations applied to shifted sets of data. And so apparently the situation is idyllic. We can get the solution. Of course, reality is almost never idyllic because if you work with real data, you will never find a common point. And so it will be necessary to introduce a suitable cost function to extract one model and so on. In the multivariable case, we have still another problem because it is not difficult to consider a model, a minimal parameterization model in which we have a decomposition of the whole model into a set of models, one for every output. They are interconnected models. And then we can apply to these models the same procedures that we can apply to the CISO or MISO processes. But the problem we get is the following. Independently from the cost function, for instance, the covariance matching or other, a lot of criteria have been proposed. Independently from the criterion that I can select, I will find different points in the noise space for the different subsystems. So I will get a set of parameters that maybe will also describe in a reasonable way my model, but I will get a collection of noise points. And a possible solution has been the following. It has been suggested by this very old building in which there exist channels that apparently point to some constellations or stars or things like that. So the idea was associating models no longer to points in the parameter space, but to directions in the parameter space. And the intersection of a line with the singularity surfaces associated to the different models will define one and only one model. Well, of course, you will say that also in this case we have different points, different intersections. That's true. But anyway, these points are characterized by an important feature, the fact that the ratios between the different variants are the same. and this introduces more congruence in the model. Well, a last consideration, if I have still 1 minute or two, concerns the optimal interpolation of dynamic sequences. In practice, we can repeat the same steps, mutatis mutandis, changing very little, and introduce again G with the parameters of the model, vector V, which in practice is the sandwiched behavior of the system, and eventually we can find the maximum likelihood estimation of V cap or the minimal variance that are given by an expression which is formally the same as in the algebraic case. Well, okay, again, can we do something useful with this expression? Well, an idea is the following. I know it's the log of NBC, and I liked it. We could, given a covariance matrix and defining its singularity surface, move on this surface. For every point of this surface, or for every direction in the noise space in the multivariable case, we can get a model and the noise covariances. With this information, we can obtain the best estimation of the vectors V cap and V tilde. And those two vectors have a nice property, that their orthogonality will be assured only in the point associated to the true noise variances. So we can introduce a new way of, a new criterion, it was not necessary really, but for a sort of, well, I will not speak about filtering, but we could introduce a new identification criteria in the errors in variables Frisch context, just by checking the orthogonality of the optimal estimations of the vectors V cap and V tilde. We have compared this criterion with other existing criteria. I must say that it is not, it works more or less the same as the covariance matching criteria, rather, with another negative point. If your sequences are very long, I mean, for instance, 10,000 samples, this becomes, from a computational point of view, very heavy. And so, while with 1,000 data, it is quite fast. It can be compared with other criteria. But so I cannot say that this is, it's just interesting from a geometric point of view to see that this orthogonality condition can be used to select a model that maybe looks a bit reasonable. So just as a conclusion, I have been able to say almost nothing using a lot of your time. So perhaps I could think switching from the academic field to the political one, but I don't intend to do so. Thank you again, Sergio.